you. Thank you very much for the invitation. It's a pleasure to be here. And this is a talk about uncertainty quantification. And actually, in the Netherlands, where I'm from, a lot of people are familiar with this idea of uncertainty quantification. And it's through this thing, speed skating on natural ice. It's a very popular sport in the Netherlands during the winter. And one of the main questions that comes up every winter is when will the ice be thick enough to hold us? And it doesn't only involve being thick enough for the ice skaters to be on the ice, but also for cars to drive out there and to maintain the quality of the ice, maybe to bring out some food and beverages. And it's an important question. And what we see daily on the national television during the winter is a plot like this. So during the weather forecast, the weather forecaster will show us this plot, and it shows us a forecast of the ice thickness for the coming days. So here, today apparently is Saturday, and the days continue, Saturday, Sunday, Monday, Tuesday, Wednesday, and here is the thickness of the ice. And what they've done, they've run a model, ran a simulation, and gotten a certain result. It's this blue dotted line here. That's the control result. But then they've taken the initial conditions of their simulation and they've changed them a little bit, and they get all these green results for different initial conditions. And what you see here is something that you might notice as well in the daily weather forecast, that for the first couple of days a weather forecast can be pretty reliable, but when you forecast further down in the future, the forecast might become less and less reliable, and you see that from the spread here in the results. So I think it's a really nice way of getting introduced and getting familiar with the idea of uncertainty quantification. Today I'm going to talk about some current developments in uncertainty quantification, and this is joint work with Richard Dwight, my former supervisor at Delft University of Technology, Brendan Harding from the ANU, who's here for us as well, Piet Hogeboom from the NLR in the Netherlands, Benoit Malot from NUMECA in Brussels, Thomas Scholz, my former colleague at Delft University of Technology, Steve Roberts, who's here as well from the ANU, and Eggy Vorneman from the Royal Netherlands Air Force. Just tonight, to get an idea of the contents of the talk, I will talk about why do we do uncertainty quantification and what is surrogate-based uncertainty quantification. And then I'll discuss only a couple of examples of common surrogates. There are a lot of ways to make a surrogate, but these are just a couple of examples. And then after that we'll dive into some of the current developments and applications. So, as engineers, I guess we are pretty familiar with the idea of uncertainty and of quantifying uncertainty. When you want to measure the length of a ball pen, you might take out a ruler and you might state that the length of the pen is 12 plus or minus 1 centimeters, right? And you might actually want to take a more accurate ruler and state that it's actually 12.4 plus or minus 0.1 centimeters, the length of the pen. And then you could go on and take more accurate measurement tools and get a more accurate result. But every time you do that, you are still facing this level of uncertainty that's left there. And this has been expressed in words by the Joint Committee for Guides in Metrology. So metrology is a discipline that takes into account how do we measure things. So it's an interesting question. And what do they say? The result of a measurement is only an approximation or an estimate of the thing that we're trying to measure. And this estimate is only complete when it's accompanied by a statement of the uncertainty. And that is what we actually just saw for the length of the pen. So we have an estimate and a statement of uncertainty. But this Joint Committee for Guides in Metrology, they say your estimate is only complete if it includes a statement of the uncertainty in the estimate. And I would say that the same thing actually holds for the result of a simulation. The result of a simulation is also just an estimate, and it's only complete when it includes a statement of the uncertainty. So, how can we quantify this uncertainty in the result of our simulation? Well, there are a couple of ways to do that, and one example is to use a surrogate. So what is a surrogate? Well, we start out from a very conventional way of looking at the simulation. We say the simulation is a black box. So we have some input going into the simulation, and we have some output, which is our quantity of interest, but we're not going to look inside the simulation. We're going to consider the simulation as a black box, which is just the input-output system. And the reason that we do it like that is that it's usually going to be very expensive if we want to try and change the solver. This is usually something complicated, and we don't want to interfere with it. So we have our parameters here, and as we saw, each parameter has some kind of uncertainty associated with it. So we can express this uncertainty on the form of a probability density function for each of the parameters. We put these parameters into our simulation, and we would like to get a PDF for the output, for the quantity of interest. Well, how can we do that? One way of doing that is doing a Monte Carlo simulation. So here we have just one random input, and we have a quantity of interest, the output, and this dotted line is the response of our system. But we don't know it is the response of our system until we run a simulation. So what we do is we have a probability density function for our input, and we sample that randomly, and we get all these results for different input values. We get the different output, and we can build a histogram of that, for example, and get the PDF of our output. So this is a really reliable way of quantifying the uncertainty in the result of our simulation. We just have the input distribution, we sample randomly, and we get an output distribution. The problem here is that it can be really expensive. We might need a large number of simulations to do this accurately. I think these are about 20 simulations, but actually to build this histogram this accurately, you need many more simulations. So what we do instead is we build a surrogate. We sample our input parameter maybe only 4 times, and we kind of interpolate our result. And this blue interpolation is known as a surrogate. And then what we can do is sample our surrogate. So instead of sampling the expensive solver, we sample this interpolation, which is a fairly simple and inexpensive thing to do. And again, we can build our PDF for the output. So that is a way of doing uncertainty quantification if each of these single simulations is just too expensive to do a full Monte Carlo analysis. Well, how can you build a surrogate like that? You can do it in one dimension, like we saw here, so for one random parameter, but you can also do it for multiple random parameters, for multiple uncertain inputs. And this is an example in 2 dimensions, where we have what is known as a design of experiment. So we sample here and there, and we get our simulation results. And the surrogate is again just an interpolation of our results. We have our input distribution, and we get a distribution for the quantity of interest. But remember, each of these dots here is actually a computer simulation. So it might be very expensive, might take you an hour or a day to compute one of these results. But the nice thing, I think, that you can recognize here is that building a surrogate is very much like building a terrain elevation map. So you have some terrain elevation data here, which are fairly expensive to acquire, and you can build this surrogate, this map, that gives you kind of a response of your system. So how can we build a map like this? There are many ways, of course, to build a surrogate, many ways of interpolating, but I will give you only 3 examples. One is to do interpolation on a regular grid, one is to do interpolation on a sparse grid, and the third example I'll give you is kriging regression. So consider a terrain like this. This is an area of Switzerland near the Eiger, one of the famous mountains in Switzerland. And here we have our parameter 1, the longitude, and the second parameter, the latitude. And we're looking at the quantity of interest, the height above sea level. And we can sample this map using a regular grid. So we can take one sample and we get this map here in orange. So that's not going to be a very accurate map, of course, but still, it's a nice map. We can increase the number of samples, the number of simulations if you want, and we get a more accurate map. And even if we increase the number of samples more and more, our map gets better and better until we end up with something like this here. So that is a very straightforward way of building a map like this, and it's also a very straightforward way of building a surrogate in more general terms. The problem here is that in higher dimensions you will be using a lot of data here. And remember, in the case of the surrogate, each of these dots is an expensive computer simulation. So what you can do is use a sparse grid interpolation. And this is just a way of introducing it. We would actually like to have our result on this fine regular grid, but instead of computing all these data, we're going to combine the results on these lower level grids. So this is our high level grid, these are our lower level grids, and by adding up the results on these grids and subtracting the results on these grids, we can actually get a pretty good approximation of the result on this grid. That's what we've been doing here. So here again we do interpolation. We try to build our terrain map. We have 1 sample, 5 samples, and the number of samples is going up. And the more samples we add, the better the result gets. Then there is another way of building a surrogate. It's kriging regression. I guess most of you are familiar with kriging, as it is a technique from geostatistics, but that has been well used in building surrogates. It was developed by Krig and Materon and Gandin. Unfortunately, I don't have a picture of Gandin. He was a guy from Russia, but he was an important developer of this technique. And when we use kriging, we get the result that looks somewhat like this. So just like in the other cases, when we add more data, the map gets more and more reliable. But the nice thing with kriging is that we can do it on a randomly sampled grid. So we can just have these random samples and we can still do our kriging regression. How good does this work? Well, this is a convergence plot for the 3 methods we just considered. These are the number of data. This is the error in recovering this map. And we see that they all converge somewhat in the same rate. Actually, the regular grid is not so bad here. But then the question is, what will happen if we add more dimensions to our problem? So if we have multiple uncertain parameters. In this case, we were looking at 2 parameters, but in uncertainty quantification, we might have 3 or 4 or more uncertain parameters. So what we can do is specify a certain target accuracy and see how many data we need to get that accuracy. And that is what we've done here for a test function. So here is the number of parameters or the number of dimensions of our problem. This is the number of computer simulations that are required to get an accurate surrogate. And this is the cost that runs up pretty steeply for the regular grid. Notice that this is on a log scale. So this is quite expensive, maybe 3,000 simulations. When we use our sparse grid or kriging, the scaling is much better. So here we're looking at maybe 30 simulations instead of 3,000, which is a big difference. for 5 dimensions. For the kriging, we've not been using this truly random kind of sampling because the points might start to cluster, so we use a Latin hypercube grid. So how can we use this? I've tried to select a couple of applications, and each of the application shows one of the current developments. So we'll have a look at gradient enhanced kriging, the gradient enhanced sparse grid, multi-fidelity kriging, and the multi-fidelity sparse grid. So we've seen that if we have an uncertain parameter here, we can sample it, we can run our simulations, and we can make this surrogate that interpolates our data. But in this case, of course, you might say that we haven't ran enough simulations. Our surrogate is just not good enough yet. And what we can do is add gradient information to our simulations. And when we do that, immediately our surrogate is almost on top of the true response of our system. Now you might say, to get these gradients, of course, we need to run another simulation, right? And that's true, but there's a nice way of doing that. Assume that we have a linear response, which depends on only d parameters. If we use only function values, we need 1 plus d simulations to get an accurate surrogate. Yeah, one simulation and then one additional simulation for each dimension, each uncertain parameter. If we do a gradient enhanced surrogate and we use finite difference based gradients, again we need 1 plus d simulations. But now there's this nice technique where we can use an adjoint based gradient, and it requires one simulation and only one adjoint simulation. And this adjoint simulation is going to provide us the full gradient. It will provide us all the derivatives of our quantity of interest with respect to all the uncertain parameters. And you might be able to imagine that if we increase the number of uncertain parameters, this can provide a major speed up of our analysis. These adjoint-based gradients, they were developed for gradient-based optimization schemes, but they turn out to be pretty useful for uncertainty quantification. So let's look at the application. This is an Airbus airfoil. It has been modified slightly because Airbus doesn't like to give out their original designs, so we don't get to work with the actual Airbus airfoil, but with the slight modification of it. And it's a transonic airfoil. You can see the shock on top of the wing and the small shock also on the bottom of the wing. So this is our computational mesh. We're solving for the Euler equations, and this is a pressure plot. And the quantity of interest here is the drag, because usually when we design an airfoil, we try, for example, to minimize the drag. What happens if we build an airfoil? We have this design, optimal design of the airfoil, a nice shape, and then we send it to the factory, and the airfoil that comes out of the factory, it's going to look different because we have manufacturing tolerances. So the airfoil that we designed and the airfoil that is going to be on our airplane are not going to be exactly the same. There's some uncertainty there. And we've parameterized this uncertainty by using shape deformations. So these are like basis functions, and each uncertain parameter is a coefficient for these basis functions. And the nice thing is that we can now increase the number of uncertain parameters gradually, going from 1 maybe to 12 to 16 or to 32 uncertain parameters. And then we've done the same thing. We try to find out how many simulations do we need for an accurate surrogate. Well, for kriging, this blows up pretty quickly, and for gradient enhanced kriging, the scaling is much better. We can express this in this form. This is again the number of random shape parameters, and this is the speed up, so the computational speed up that we get by using our adjoint solver to get gradients. And you can see that the computational speedup roughly scales linearly with the number of random shape parameters. So this is a really nice property. It means that when we make our problem more complicated, we add more random inputs, more uncertain parameters, that we get a higher computational speedup. Just to show you what kind of results we get from an analysis like this. Over here is the drag coefficient, and this is the drag coefficient that we would get for an undeformed wing, so our drawing board drag coefficient. And then if we include these random shape deformations, we get the PDF for the drag, and it looks somewhat like this. And what is important to note is that in most cases the drag will be actually higher than the drag we designed for. So usually if you design a system for optimal performance, if you then go and do some uncertainty quantification, the performance will usually be worse than what you designed for. So we can do this gradient enhanced approach with kriging. We can also do it on our sparse grid. This is our normal sparse grid interpolation as I introduced it before, but here we can add other basis functions and actually add the gradient information in here and in here. So this is a drawing for 2 dimensions, but we can do this for a higher number of dimensions as well. And what we will do is we have in each of these figures we add these results and subtract these ones, but then overall we add up these results and again subtract this result, and that will give us a gradient enhanced sparse grid. And we have a test case here, which is the Rosenbrock function. In 2 dimensions it looks like this, and you can see here that the convergence of the gradient enhanced sparse grid is much better than the convergence of the sparse grid approach without using gradients. And again we can look at the scaling. So this is the cost for the sparse grid without gradients, which runs up quickly with the number of uncertain parameters. And this is the cost of the gradient enhanced sparse grid, which is much lower. There is a problem with using adjoint-based gradient information, and that is the noise. So, of course, we're talking about uncertainty quantification, and we know that noise is everywhere. But when you have noisy values, it's usually fairly easy and you know how to deal with them. When you have noisy gradients, they can really mess up your interpolation by quite a lot. And that is something that we've quantified here. So here is the relative amount of gradient noise. This is the result of one of our sparse grid interpolations on the Rosenbrock function. And this is the result of the gradient enhanced sparse grid. And you can see that the gradient enhanced sparse grid is much more accurate when there's relatively low gradient noise. But then when we start increasing the gradient noise, the accuracy starts to deteriorate. And this is something that we still have to deal with. For gradient enhanced kriging, we know how to deal with the gradient noise, but for the gradient enhanced sparse grid, we're still looking for an answer to that problem. Then there's the multi-fidelity approaches. We have multi-fidelity kriging and multi-fidelity sparse grid. So again, if we look at the kriging surrogate of this function, so this is a test function, that is the response of our system, and here are a couple of expensive simulations, and this is the surrogate that we can use to approximate our function. As you can see, again, we might say, okay, we need more samples here to get an accurate surrogate. But there's an alternative to that. We might have a so-called low fidelity system, which kind of mimics the response of our high fidelity system. And when we do a large number of simulations on our low fidelity system, we can actually use it to update or calibrate our high fidelity results, and we get the surrogate in this shape. So to summarize that, we have a high fidelity simulation, and the high fidelity simulation is very accurate, but it's also very expensive. And also we have a low fidelity simulation. It is less accurate, but it's also pretty cheap. And we try to combine those two. And basically what we do is we say we have this high fidelity simulation. The high fidelity simulation is the sum of the low fidelity simulation and the difference process. And the assumption is that this difference process is relatively smooth with respect to changes in the uncertain parameters. And when that assumption holds, we can make a multi-fidelity interpolation of our simulation results. So as an analogy, we can go back to the map making, and we can use our multi-fidelity approach here. Because what we could do is we look at space shuttle data for the height of the terrain, and the height of the terrain is given as at these dots. So we have a fairly expensive way of measuring the height of the terrain by sending up a space shuttle, and also we don't have very many of those measurements. They're very sparse in a way. But then the other thing we can do is send up a fighter jet and take pictures of the terrain. And in this case, the pictures that the fighter jet take, they have an overlap in this area. And in this overlap, we can use stereo matching to get an approximation of the height of the terrain. And these results are relatively cheap to obtain. They're on a very fine mesh, and also they're quite inaccurate. Actually, the stereo data that we get are just relative heights. We don't even know the absolute heights of those results. But when we use multi-fidelity kriging to combine those results, we get a terrain map like this with a lot of detail. So that's just as an analogy. When we use this for uncertainty quantification, we can look at the sailing yacht hull. And in this case, there are three uncertain inputs: the mass of the hull, the center of gravity, so is the center of gravity here or more down to the back, and tank blockage, because we're looking at towing tank results in this case, and when the hull moves through the towing tank, there's a certain amount of tank blockage, but actually we don't know how much tank blockage there is. So these are the uncertain inputs, and the outputs that we're looking at are the resistance of the hull, the sinkage, so how deep is the hull in the water, and the pitch, so the forward angle of the hull. And we work on a coarse mesh for the low fidelity results. This mesh takes us about 15 minutes to compute a result, and we do a lot of solves, 120 solves. And also for the high fidelity result, we work on a fine mesh. Takes more than 2 hours to run, but we do only a limited number of solves, 24 in this case. This is a typical result that we get. Here's the hull with the waves it creates, and these are the waves drawn on the hull. And when we do these simulations, the low fidelity simulations and the high fidelity simulations, and we combine them, we can get the result like this. So this is, for example, the resistance. This black line is the average, the mean of our CFD results, and the gray area is plus or minus 1 standard deviation. So this is how we've quantified the uncertainty in our computer simulation. And you can see that for these lower speeds, the uncertainty is pretty small, and the results of the computer simulation are almost on top of the experimental results, whereas for these high speeds we get some other effects that are going on in the towing tank. The uncertainty grows, and also the difference with the experimental values starts to increase. Then we can do the same thing as we did with kriging. We can talk about a high fidelity simulation, which is expensive but accurate, and a low fidelity simulation, which is inexpensive and less accurate, and we can use it on our sparse grid. And we will have a look at the sparse grid. It's hard to look at the sparse grid in one dimension, but this is roughly what it would look like. So over here we have the high fidelity process, the dotted black line, and we sample that with our high fidelity simulation. And because those are expensive, we only do a couple of them. And then we have our low fidelity results, and because they're pretty cheap, we can do a lot of them. And by combining them, we get our multi-fidelity interpolation, the red line, which is pretty close to the high fidelity process that we're interested in. We've used this for the Okushiri test case. I think a lot of you will be familiar with it. It's actually a scale 1 to 400 wave tank model of an actual tsunami that occurred on the coast of an island of Japan. And the solver that we use here is a NuGa. It was developed as a cooperation between the ANU and Geoscience Australia. And the results that I'll show here are pretty new. They're from this month, and they were computed on the region cluster. I think some of you are working with that as well. So what we have here is a map of our area, and here is the area of interest, a couple of gullies here on this side, and from this side we get an incoming wave. And the incoming wave looks like this black line. That is the input. And the output is actually the level of the water on top of the land in this area over here. And it looks somewhat like this. So for a long time nothing happens. There's just zero water on the terrain. And then all of a sudden we get this flood wave. So what is uncertain about this? Well, actually when this tsunami comes in here from the left, we might not be quite sure about the shape of this incoming wave. So what we do is we fit a bump over here, and this is going to be the basis function for our first uncertain parameter. And the uncertain parameter is just the height of this bump. And then we can add maybe later on a second bump and a third bump and so on. So there's some uncertainty in this input, and we want to know what is the effect of this uncertainty in the input on the output. Is it uncertain as well? This is just some grid, these are some results for the mesh convergence. So here we have the result on a very coarse computational mesh with only 256 cells. And if we increase the number of cells, our result converges. So this line that I'm showing here is actually our output. So this output is this line. We have zero water in the area of interest, and then we have this flood wave. Interesting to notice that the waves are slower on the coarser meshes. So when you are on the coarser mesh here, the wave arrives slightly later than when you're on the fine mesh. So that's an important difference between the low and the high fidelity result. This is the computer cost for running a simulation on one of these meshes, and you can see that the high fidelity mesh that we use takes about 1 hour to compute a result, whereas the low fidelity mesh takes only 1 minute to get the result. So that's a big difference. This is, I'll show you what this is. If you have this output, this is actually for the undeformed incoming wave. And this output is what you see in this transact here. So there's no water coming in, and over time you get this flood wave. But here on this axis we're changing the relative bump height of this first parameter. So this is for only one uncertain parameter. So if we increase the height of our incoming wave of this bump, then we also increase the response. And if we decrease the incoming wave, we decrease our response. And really, you can think of this one, this relative bump height, of having a PDF here, and we try to propagate that uncertainty. This is the high fidelity output, and this is the low fidelity output. And as you can see, if I skip back and forth, there's this delay here. So what we have to do is correct for this delay, and that is something that we do here. This is the relative bump height, so that is our uncertain parameter. In this case, we're still looking at one uncertain parameter, and this is the time scaling that we use to correct for the change in wave speed. Of course, we can only do that when we know the difference in wave speed, and we know the difference in wave speed only at a couple of locations here where we have a high fidelity and a low fidelity result. So in this case, we have 3 high fidelity simulations. We can compute the time scaling that we have to apply there. That is going to be our correction. And for the other values of our uncertain input, we just interpolate. This is what we're looking for. Uncertainty quantification for the output. So this is again the time, but now our flood wave here has some uncertainty there, the 10 and the 90% quantiles. And this is for a lot of high fidelity solves. I think these are 128 high fidelity solves, each taking an hour. And the question is, how can we approximate this result using the multi-fidelity approach? Well, this is the same high fidelity approach I showed you. This is a multi-fidelity approach associated with this dot, which I will soon discuss. And you see it's almost the same, only maybe over here there's a small difference. So what we can do is we compute the error of this multi-fidelity output with respect to the high fidelity output, and we plot that error. And when we do it for only the high fidelity simulations, we get this blue line. So this is just one high fidelity simulation, 3, 5, 9 simulations. And the error gets smaller and smaller with respect to this reference of 128. But what we could do here, if we have 3 high fidelity simulations, instead of adding more high fidelity simulations, we could also start adding our low fidelity simulations. And there we see that the result converges much faster up to a certain limit. So again, we can ask ourselves, if we have a certain target accuracy here, how many solutions do I need? How many code runs do I need if I increase the number of uncertain parameters? And that's what we've plotted here. So this is the number of uncertain parameters. This is the cost of the uncertainty analysis if we use only high fidelity simulations. And this is the cost of the uncertainty analysis if we use both the high and the low fidelity simulations. So what you see here is that when you start increasing the number of uncertain parameters, it might be interesting to use this multi-fidelity approach, because it's, in this case at least, it's just much cheaper. So as a conclusion, I think you could state that a result without quantified uncertainty just isn't a result. You really have to quantify the uncertainty in your result. Surrogate-based uncertainty quantification can be a relatively cheap way of doing that, but even with surrogate-based uncertainty quantification, you might run into this curse of dimensionality. So that's the exploding number of simulations that are required when you increase the number of uncertain parameters. And if you want to address that problem, there are a couple of ways, but 2 of them I showed here today. One is to use gradient enhanced surrogates if they are available from your solver, and the other one is to use multi-fidelity surrogates if at least your high and your low fidelity simulations have a relatively smooth difference. Thank you for your attention, and perhaps there are some questions.
Okay.